1.4 Roots of Quadratic Equations. So for real numbers a, b, and c, if the roots of the quadratic equation az squared plus bz plus c equals 0 are non-real complex numbers, they occur as a conjugate pair. So for example, if we had a root, say we had a root of quadratic, if a root was say 3 plus 4i, another root would be the conjugate pair 3 minus 4i. So for example, if we look at a normal quadratic, let's say x squared plus 4x minus 5 equals 0. When I factorize this, we would get x plus 5 and x minus 1 equals 0. So we know our roots to be x equals minus 5 or 1. And then likewise, if we knew the roots using our factor theorem, we can then go the other way and go, well, x plus 5 and x minus 1 would be our sort of two factors, and then we multiply them equals 0. So we can use this information when dealing with quadratics. So some notation to look at: when we're dealing with roots of complex varied polynomials, we can use Greek letters such as alpha, beta, and gamma. So if, for example, we had the roots for quadratic, we went for alpha and beta, if they are my two roots, we can write our quadratic as x minus alpha multiplied by x minus beta. That equals 0. And we know that when we multiply them out, we get x squared, and we take away the sum of those roots, and we add the two roots multiplied. So beta there. Okay, so let's have a look at a question. Well, actually, before we do that, I'm going to leave out two proofs for why they come in why the roots come in complex conjugates. You'll notice I will struggle to pronounce this word, and I will do another video fighting this out later. But you can pause this now and give it a read. Okay, so let's look at a question. So if one of our roots is 7 plus 2i, and this comes with real coefficients, what is the other root? Well, it will be the conjugate pair. So the other root, beta, is 7 minus 2i. Okay. So find the quadratic equation. So I'm going to do the slower way first, and then I'll show you a quicker way after. So the slower way. So we've got our two roots, 7 plus 2i and 7 minus 2i. So using the factor theorem, we can write it as the following. I'm going to do z take away alpha, and z take away beta equals 0. So I'll get the following: z take away alpha would be 7 plus 2i, and z minus beta 7 minus 2i. That equals 0. I'm just going to make this a bit smaller. So we're going to multiply it out. So we're going to get z squared, and then minus 7 minus 2i times z, and then same idea here, minus 7 plus 2i z, and then we got two negatives multiplied, so we can plus 7 plus 2i times 7 minus 2i equals 0. Okay, so we need to clean this up quite a lot. So we're going to get z squared minus 7z plus 2iz minus 7z minus 2i z plus 49. They're going to cancel out, and then you're going to be left with minus 4i squared equals 0. Okay, they cancel out here, and I think that's all I can see. So you're left with z squared minus 14z plus 49, and then minus 4 times minus 1 becomes plus 4 equals 0, and the quadratic is the following: plus 53 equals 0. There we are. Okay, a quicker way to solve this, I'll change to a green. So that's our answer there. So just to remind you, we had our two roots. And what we know is when we combine them up, the quadratic will be the following. Okay. So we can recall that when we multiply them together, so a plus bi, a minus bi equals a squared plus b squared. So in this case here, you're going to get 49 plus 4. So we will get that 53 there. Z squared. And then when we add them together, you're going to get 14. And there we are. So minus 14z. And that's a quick way. So good to know both ways, but with enough practice, you can just skip to that quicker method there. All right. So here's a question to test your understanding. So this is where I would pause the video and have a go at it. And now I will monitor it. So given that one of the roots is 2 minus 4i, what's the other root? It'd be 2 plus 4i. You can write that as Z2 if you want. Okay. So find the values of P and Q. Okay. So we have the following. We've got two roots. So 2 minus 4i, 2 plus 4i. So we've got the following: z squared minus our two roots added plus our two roots multiplied equals 0. So we get z squared minus, when we add them up, we're going to get 4. Let's put a z in there. 4z. And then multiply together, you're going to get 4 plus 16, so plus 20 equals 0. And there's your answer. I'll write that a bit neater. Z squared minus 4z plus 20 equals 0. So there's our quadratic there. P and Q. P would be -4 in this case. P equals -4 and Q is 20. So there we are. Okay, so now have a look at exercise 1E. I will have a look at the hardest question in that. So you can pause this now and give it a go. And I will now solve that last question, question 9 I've got here. So given that z equals 5 plus qi is the root of the following: z squared minus 4pz plus 34 equals 0. P and Q are positive real constants. Find the value of P and Q. Okay. So we've been given one of the roots. So if one of them is qi, the other one will be minus qi. Okay. So we could write it out. So we've got z minus 5 plus qi multiplied by z minus 5 minus qi. Okay. So when we come to multiply it out, we're going to get z squared minus our two roots added together plus our 2 roots multiplied. Okay, so z squared minus, when I add them up, I'm going to get 10 z, and when I multiply them, I'm going to get 25 plus q squared. 25 plus q squared. Okay, so what I can see here, 25 plus q squared, that equals 34. I'm so matching up our coefficients. So 25 plus q squared equals 34. Q squared equals 9. We're told it's a positive in the question, so q has to equal 3. There we are. And we can see here minus 4p equals minus 10. So minus 4p equals minus 10. 4p equals 10. Therefore, p equals 2.5 or 5/2. And we're done there. Okay, there you are.